Welcome to the next video in the Discrete Math video series, and in this video we're going to solve these exercises. So 2 is even and 3 is even, right? Those are our two sentences, and so this naturally translates to 2 is even but not 3. That's a pretty natural translation. Okay. Effectively, let's just say that this means that 2 and 3 have the same have different parity, right? So if XOR basically means that the two sentences have sort of mismatched truth values, and they're both talking about 2 is even, 3 is even, then by XORing them, that basically means that they don't have the same parity. Parity means even or odd, right? So this is saying the parity of 2 is even, the parity of 3 is even, and so by saying that they're not both true, it means like they don't have the same parity, that they are either not both they are not both even and not both odd. So anyway, so that's one way to express this. You don't have to do it this way, but a particularly slick way is to use this phrase of parity. And so A XOR B means they don't have the same parity, and then when you negate that, you're saying that they do have the same parity. So this says 2 and 3 have the same parity. Okay, and let's move on. Let's reveal this. And so this one is saying that it is not the case that both 2 and 3 are even. So we could phrase that as 2 and 3 are not both even. That's a nice natural way to express that. Okay. Now let's look at truth tables for complex propositions. I'm getting a little out of order with the textbook, but I think this is maybe kind of important to do it a little earlier. At least in my opinion, I would like to get to this earlier than the textbook does. So let's look at a complex proposition like this, and let's build the truth table for it. Now, we have seen that if you have a proposition that has only a single propositional variable, you only need 2 rows. If you have 2 propositional variables, then you need 4 rows, and it turns out that if you have 3 propositional variables, you need 8 rows. Every time you get a new propositional variable, you need to double the number of rows. And, effectively what, sort of the reason why it goes that way is that you basically need to think about, let's just say all of the possibilities for A, which are true and false. But within the possibilities for A being true, right? So you're basically going to have kind of 2 regions for A, right? Your A is going to have a true region and a false region in the table. But then inside of the true region, B is going to have a true region and a false region. So it's now got to eat up some extra truth table rows that way. And then, also it's going to have a true region and a false region inside of each of A's true and false regions. And then C, it also has to get a true region and a false region inside of all the others, right? So then it's going to get a true region and a false region and a true region and a false region in every one of the already existing regions. And so that kind of explains, every time you sort of include an extra variable, you need, if we were to put onto here an extra variable D, then we would need to have all of this where D is true, and then we'd have to reproduce it where D is false, right? So you kind of double the number of rows you need each time you add a variable. So in any case, at the end of the day, what we're doing here in this exercise is just doing the truth table for the sentence, and so I just wanted to explain why we have to have, in this case, 8 rows to the truth table. Now, I do what I always do, which is to take A and transcribe all of its truth values. I take B and transcribe all of its truth values. Likewise for C. So this is a mere transcription of what you already see over here to the left of the table. From here, we need to have our logical symbols operating on the given truth values. But there's a little bit of a subtlety this time, because if you look at if you just read left to right, then the first symbol you encounter is a negation. But keep in mind that that negation is negating, because of the parentheses, it is negating the entire conjunction, not A, not B, the conjunction of them. And therefore, right, it should be reading its truth values off of the truth values that are for the conjunction. But we don't have those truth values yet, so you can't do this left to right. You have to go to the sort of, in some sense, the lowest level, sort of logical operator and build it first before you can get to that negation. So we need to fill in the conjunction next. Okay, we're going to use the rule that true, true gets true, right? This is the conjunction rule. True, 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 false, false, true, false, 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 true, false, false, true, false, 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 false. Now that we have these truth values, we can finally come over to this negation and negate those values, right? So this true gets negated into this false. The true here gets negated as false there. This is true because that is false, and so on. So true, 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 true. Okay. Where the negation is reading its values from everything under the conjunction. Okay. Next, what is next? Well, I guess there's only one thing left, which is this disjunction. And this disjunction is going to read from its left. Okay, what is to its left? This whole thing is to its left, meaning that the value for the disjunction, right, this disjunction reads its values from this column on the left, because that is the sort of main operator, you could call it, on the left-hand side, and it's going to read its values from this column on the right, because that is the main thing on the right, namely, really, it's the only thing on the right, but so hopefully you get the idea that when you work on a binary operator, it's got a thing to the left, and you have to identify what that is and go to its column, and it's going to have a thing to the right, and you have to identify what it is and go to its column. Okay, so that's in general how you do these truth tables. Let's fill this in. By the way, let's now do it in the way that I think is fastest. I just feel fast when I do it the following way. I say that the disjunction is false when both sides are false. Let me go look for places where both sides are false. False, false. So I know that there, the disjunction is going to be false. Okay, I'm looking again for like false, false. No, right? Like I'm scanning this table and I'm not seeing false, false. So in fact, that is the only place where on the left you get false and also on the right you get false. And therefore, everywhere else it must be true. That's the rule for disjunction. So now I just kind of thoughtlessly fill in all the other spaces with a true. So that's a nice fast way to fill in disjunction, is to look only for the rows where both sides are false. When that is true, you mark that place in the table as a false, and then just thoughtlessly fill in all the remaining spaces with a true. The similar rule works for conjunction, right? You can look for all of the rows where both sides are true. That would be here, and you fill in a true, right? True, true, fill in a true. Then keep scanning, looking for all places where both are true, but you don't see any. So you would just fill in true, true, right? Looking for the places where both sides are true. Once you've filled those in with trues, everything else must be false. That's, again, the rule for conjunction. And just thinking in that way, I feel, is faster. So you may want to follow me in doing that. But, everything here is kind of, whatever works, whatever you prefer. So anyway, we've already kind of remarked on why it is that when you have n propositional variables, like if it's one propositional variable, you have two rows. If it's two, right, if n is equal to 2, you've got two propositional variables. Then you have to use 2 to the 2, which is 4 rows. And then if you had n equal to 3, that's 3 propositional variables, you would get 8 rows. And if you had 4 propositional variables, you'd have 16 rows, and so on. Okay, anyway. Let's then introduce this exercise, and we'll solve it in the next video. Do the truth table, right? Construct the truth table, which is, I think, essentially the same as the previous one, except that I am just taking the negation that was on the outside of these parentheses and moving it onto the variable a. Sort of the promise here is that that should probably, not always, but usually that changes the truth value of the sentence. So you should see that when you generate this truth table, there are at least a few places where the values do not match what we got here. Oh, I should also emphasize the the true value, the true truth table in a certain sense is that last value that you fill in. It's the values under the main operator that I'm highlighting now. In a certain sense, everything else is just build up to that, right? So the true truth table, what it's actually asking for when it says to construct the truth table is really kind of just this last column, but everything up to that was needed as a kind of computing all of the intermediate values so that we could build up to that. That, though, is the actual answer to the question. Okay, and so with all of that in mind, please solve this exercise and then play the next video.